the functions that have the variable in the exponent are called exponential functions. The exponential functions have horizontal asymptote. We will look at the examples. We'll see all of these. For now, just write it. So horizontal asymptotes. Now, you see the generic formula, or this is not the most generic formula, but you see y equals b to the power of x. Y equals b to the power of x. This number b is called the base of our function. And when the base is greater than 1, we call that exponential growth. Because think about it, when in the example that we just considered, we had y equals 2 to the power of x. So every day my money doubled, right? So it's the exponential growth. When the b, on the other hand, is less than 1, we call that exponential decay. And think about it, if instead of 2, I had y equals 1 over 2 times x. What happens if every next day my money are not doubled? It gets cut in half. So my capital is kind of diminishing, right? So that's why it's called exponential decay versus exponential growth. So if you don't know, if you just want to determine whether your function is exponential growth versus decay, and you don't have the actual equation, so you don't know what b is exactly, you can also look at the graph. So for the exponential growth, if you look on the right end behavior, as our x goes to infinity, the graph will go away from its asymptote. Right, so for this kind of function, the one that you just looked, on the right, the function will go away from my horizontal asymptote, in this case, just y-axis. You see how it goes infinitely up. But for the decay, on the other hand, the graph, as we look at the right-hand behavior, you will see the graph going towards the asymptote. So for this kind of function, you'll see something like this. On the right, my graph goes closer and closer to my asymptote.
So it depends on where the arrow is.
Well, not arrow, like here, right? So on the right, always just the right-hand behavior.
So the right
For
side.
the growth, my function will go away from, like, either to plus or positive or negative
So it goes
infinity.
to the right and the left.
On the right end. And for the decay, when my b is less than 1, then my function will get closer and closer to a particular asymptote, a particular horizontal line. Yes?
Does it ever cross the asymptote?
No. It will never cross the horizontal asymptote. Questions? Okay, let's look at the example. Uh-oh.
It's the same
The
one.
same thing. Okay, so let's look at these two graphs. This graph y or function y equals 2 to the x. Exactly from our fourth problem, right, in the beginning. So let's graph this one just manually with creating the data table. And then we'll use the calculator after that, but for now let's just do this manually. So I can choose any axis, right? So I'll just choose -2, -1, 0, 1, and 2. So let's start from the bottom. If x is 2, then y is what? So if x is 2, then my y equals what? 2 to the power of 2, which is 4, right? So 4. Easy. If my x equals 1, then my y equals what? 2 to the power of 1, which is 2. If my x is 0, then my y is what? 2 to the power of 0 equals what?
2.
1.
1. Everything to the power of 0 is 1. Any number to the power of 0 is 1. Now, what happens when the exponent becomes negative? Y equals 2 to the power of -1. How do we deal with negative powers? Yes, so numerator becomes denominator. We flip it, right? So 1 over 2 to the power of 1. So it's just 1 over 2 is half, 0.5.
If you enter 2 to the power of -1, will it come out like that?
Yeah.
It'll be that.
Yeah.
One
So,
fourth.
negative, not 1/3. 1 what?
1/4.
1/4. So if my y or my x is negative 2, then I have y equals 2 to the power of negative 2, which is the same as 1 over 2 to the power of 2, which is 1 over 4. So 4 and 25. See what happens? Right? I'm flipping it. So for the negative exponent, my result becomes less and less than 1. Yes, and it gets closer and closer to 0. But can I ever find x such that it will give me y equals 0? No, right? Because x could be very, very, very like large negative number, like minus million, negative million, but it still will just be 1 over 2 to the power of millions. It still will be positive number. It will be very small, but it still will be positive, right? It will always be positive. Yeah. So let's plot this point. 0, 1, 1, 2, 2, 4, and then 3 would be what? Double, right? So 8. So I'm always doubling my y. So if I connect these points, this is the graph that I get. This is the exponential graph.
So we put growth on the line.
So is it growth or decay?
Growth.
Growth. And how do we know?
It's going up towards positive infinity.
Yes, so first of all, on the right, my graph goes away from my asymptote, which is what? What is my horizontal asymptote here? Do we see it? What is my horizontal asymptote? 0, right? I'm getting closer and closer to x-axis, which is y equals 0. That's the formula for that line. But I never cross it. So y equals 0 is my horizontal asymptote. On the right, my graph goes away from the asymptote. That's how I know it's growth. What is the other way for me to determine growth versus decay? Just by looking at the formula?
If it's greater than 1, it's growth. If it's
Yes.
less,
What is my b here?
it's
2. And so since b is greater than 1, I know that this is growth. Questions? Very nice. So let's look at the second one. Let's do this one by hand also. I just want you to understand what happens here. So let's choose our axis. What is my b, by the way? My base.
1 over 3.
1 over 3. B is 1 over 3. So we know this would be what? Decay or growth?
Grow. Decay.
Decay. Because b is less than 1. Perfect. So let's choose our points. Negative 2, negative 1, 0, 1, 2. I don't know, I just did it. Okay, so now let's look at this calculation. So if x equals 0, then y is what? 1 over 3 to the power of 0 is what?
1.
1. Always, right? 0, 1. Doesn't matter what my base is, and I take the number to the power of 0, it will be 1. What if x is 1?
1/3.
Yes, so it's 1/3 to the power of 1 is just 1/3.
1/9.
Yes, so for 2, that would be 1/9. And for 3,
1/27.
1/27. Perfect. See how we are getting smaller and smaller, closer and closer to 0. Do we see this? The higher the x, the closer will my y get to 0. What about on the other side? Negative 1.
Green.
Yes, so y, if x is negative 1, that my y is 1 over 3 to the power of negative 1, and we know how to deal with the negative exponent. We flip the fraction. So it's 3 to the power of 1, which is just 3. Do you see this? Lily, are we good? And so what would be the y of the negative 2? 9. So it's kind of flipped, right, across the y-axis. Perfect. So let's plot it. So what do you think my horizontal asymptote here will be? Again, y equals 0, right? Because I'm getting, on the right here, I'm getting closer and closer to 0, but will never reach it. So my horizontal asymptote will be x axis, and then my point 0, 1, and then negative 1, 3, 9. Let's make this something like this. Questions? So far, so good. Hmm? Can you go to the next one? Okay, so now, what if I don't know if we already learned this, but just in case, this can get a little bit confusing. So look at these graphs and decide whether it's growth or decay.
Which one is decay?
The first one is growth or decay. Who thinks it's decay? Who thinks it's growth? So why decay?
Because it's going to negative infinity.
But is it going to? Yes. Yes, exactly. So this is very important. See, my horizontal asymptote is still x-axis in both of your cases, or something close to that. And you see on the right, right here, my function goes away from the horizontal asymptote. So the growth is kind of confusing, or I guess not very intuitive at first if you think about it. You know,
So they're both.
yeah, it's decreasing, but it's growth because the growth and decay is all about magnitude. It's not about value, but magnitude.
So they're both decay.
No, so
First
this
one's
one is
the
growth.
second one's
That's
decay.
That one's growth.
Yes, so this one is growth because my line goes away from the axis. And think about what decay, the word decay means. It's kind of the value diminishes, right? It kind of becomes constant. Here it doesn't. Like thinking about money, right? So this function was about how my investment grows if I invest in Apple, right? It will grow exponentially. It will grow very, very fast at some point. When you think about example like this, what this would be,
How many like trees in the forest are getting cut down?
well, that's not a good example. Why? Because that one has the cap, right? The floor. It cannot just become negative forever and ever.
Well,
How much
think
more are you
of it
going
as
into debt?
There is a finite number of trees in the world, so there has to be like stop to it. You know what I mean? Yeah.
How much you're going into debt?
Yes. So, for example, if you buy Apple, right? This is, and if Apple really doubles every day, at some point you'll get infinite amount of money. Yes, and it will grow so fast. But if you buy it from me and I don't have it, it means I'm shorting it. I'm betting against the Apple. My debt will become infinitely. If I'm betting against Apple, right? You will be in infinite, but if I don't ever stop, I will lose infinite, right? They'll come after my children and my grandchildren. So that's exactly the like in finance, that's what happened in 2007. You were very, very little. But when hedge funds and investment, those investment funds, they were getting out of business exactly because that they never stopped and they shorted a lot of, they use short positions a lot. That's exactly what happened. This is the function that shows you how fast you can lose because it becomes so steep. Just in one day you can lose millions and millions of dollars. Right? Okay, so growth, because we are going away from, see, goes away from axis, or not axis, axis. And here, do we have decay or growth?
Okay.
Decay. Because by magnitude, my my investment diminishes kind of. It comes closer and closer to a particular constant. Yes? Do you understand? Okay, so now to like the most generic form of this exponential function. So if we start with the parent function y equals b to the x, where b is my base. So b is base. Yes? If my parent function is y equals b to the x, either 2 to the x, 3 to the x, yes. I know, you know what, the printer in the library is not working today, so you have to make sure that you write down whatever is not clear on your paper. I'm really sorry about that.
What is that symbol above this? Yeah, that, no, go on.
Here A, yes, so here A, yeah, A, this is B for base, H, K, horizontal asymptote, HA, right, we called it. This is domain and range. A, B, H, K, horizontal asymptote, domain and range. The printer in the library is not working. One particular. Okay, so if I start with the parent function y equals b to the x, so immediately from my base I know whether it's growth or decay, right? So b greater than 1 growth, b less than 1 decay. Okay, so now remember how we always talked about transformations, our numbers a, h, and k. So what does my a do to my parent function? If I multiply my function by number a, yes. So first of all, the sign, yes. If the sign is negative, it's what? Reflect. Reflect. How to reflect? And then if it's, then we look at the magnitude. So if A is greater than 1 by magnitude, then it stretches. And if A is less than 1, then it compresses. I put absolute because it's by magnitude, right? I care about magnitude, so I don't have to think about like positives, negatives there. You see what I mean? Yeah. What? Negative, yes, so negative. Put like A minus less than 0. So what about H? What does H do? Uh-huh.
Oh, never mind.
Never mind, okay.
Does it have to do with the exponent?
Compress is less than 1, yes.
Does the h have to do with the exponent and what it does to the number?
Right, so remember, what doesn't matter what function, right? If I start with the function f of x, and then I change it to f of x minus h, how does this affect my graph? Left and right? If I'm replacing x with x minus h. Remember? It's left, right, then I'm replacing the x. So if x, assuming that h is positive, so if x minus h, then it goes left or right? Right. And then if x plus h, then if x plus h plus, then it goes to the left. So same kind of transformations always work the same way. So what if I add the number k at the very end? Up or down? So if it's k, if plus k, then it's up, right? If it's minus, then it's down. Okay. So now let's think about it without even examples. If I start with the function y equals 2 to the power of x, what was my horizontal asymptote? Y horizontal asymptote was y equals 0, the x-axis. What if I say y equals 2x plus 2? What should I do with my graph, the whole graph? The whole graph goes up. So what do you think the new horizontal asymptote is? 2, y equals 2. So can we now generalize? What is the horizontal asymptote formula for this general function? Y equals k. Yes, it's just the number k. Because it moves it up or down the whole graph together with that asymptote. Questions? Very good.
What about the domain range?
Huh?
Domain and range.
Yes, so domain and range. What do you think domain is for any of these functions? For all of these functions?
And negative infinity or infinity?
Yeah. Because think about it, there are no domain restrictions, right? I can choose any x, positive, negative, 0. I can still calculate 2 to the power of x, right? There are no restrictions on my domain.
How do you find it?
Huh?
How do you find it?
So negative infinity to infinity for all these functions. Because there are no restrictions on x. I can choose any x. I can always calculate that power, right? That exponent. Or take a to the power, I'm sorry, take like 2 to the power of x. Or, yes? We looked at it already. What about range? What do you think the range is?
Everything in the horizontal
Everything
asymptote.
except the horizontal asymptote.
Yeah.
So there is something about the horizontal asymptote, right? Right here, what is the range for this function, for the third example? Negative infinity to the horizontal asymptote, right? What about here? What is the horizontal asymptote for this first example? Not horizontal asymptote, sorry. What is the range for this?
Horizontal
Horizontal
asymptote.
asymptote to infinity.
Yeah, very nice. So it's always either k to infinity or negative infinity to k. The first one if my graph is above horizontal asymptote, and this one is when it's below. So what does it depends on? Which of these numbers, A, B, H, or K, will tell you exactly is my graph below or above my asymptote, my A, right? If the A is positive, I'm above the asymptote. If my A is negative, then it's reflected and my graph is below the line. Everybody sees that? Yes? Questions about this? No?
Here we go, lunch.
Okay. So now we will just play around with all these graphs, and the first 5 are like so simple, you wouldn't believe it, because I take one of these functions and then I just apply few transformations to them, just to
Build a basic.
yeah, just drill and transformations pretty much, right? So you look at the nodes that we just made and you use them, and let's see what happens. So the first function is quite simple, almost the same as the other example that we just did. Y equals p to the power of x. So before we even plug it into calculator, what is my parent? What is my b?
3.
3. That's my base. B equals 3. So what is my parent function? Yeah, y equals b to the power of x. There are no transformations, none. Doesn't apply, not applicable. This is the parent function. So do you think it's growth or decay? Growth. And why is that?
3 is greater than 1.
Exactly. B is greater than 1. B is greater than 1. What do you think my horizontal asymptote will do? 0. Y equals, it's a line, don't give me just number. Y equals 0. Yes. Yes. What is the domain of this function? All real numbers. There is no restriction on my x. I can choose whatever I want and I will be able to evaluate. What is the range?
All numbers except
0 to, right? Because we already determined that horizontal asymptote is y equals 0, right? So this is my horizontal asymptote. So my function will get very, very close to it, but will never reach it. And it will be above or below my horizontal asymptote?
Above.
Above, because there is no negative in front. So the range is what? 0 to infinity. My k number is 0, 0 to infinity, yes? And my y-intercept,
0.
if I don't have the graph, how do I find it?
Plug in your x.
Yes, so for y-intercept, x is always what?
0.
0. So I know it will be 0 something. And how do I find that number? I just plug in 0 here. So 3 to the power of 0 is what? 1. Yeah? So now let's graph it. So two ways to graph it. Of course, we can use calculator or we can do the whole data table, right? But if you just want approximation, how would we do this? First of all, I know my horizontal asymptote, yes? Right? And I know by looking at growth versus decay, growth means it will be like this or like that, yes? Yes?
Yes.
Growth, because on the right it will go away from my asymptote. And this kind is when it's above the asymptote, so when my A is positive, right? And this one when my function is reflected, so A is negative. So for this particular one, I know that I'll have something like this going on. So just find like one point, always easy to use 0, so 3 to 0 is 1. So I kind of can plot that point 0, 1, where is it, 0, 1 right here. And I know that something like this, my function should look something like this, yes? If I just wanted like approximation.
So can you put approximations? You don't have to graph it.
Well, for our tests, Mrs. Osborne, we just said how can we use the properties and just to graph like the rough approximation. That's what we usually do, right? And for the test, that's good enough. If I see that you used at least one good point, like this one, right? And then you use the properties to determine the shape, I think that's good enough for us. Sometimes it gets harder and harder, you know, depending on. Thank you. Depending on how many transformations. So sometimes you just want to double check yourself with the calculator, but you know, let's just plug it in into calculator to learn how to do this. So as always, we go to y equals, right? And then was it 2 or 3? 3. 3 to the power of x. So nothing
You
fancy.
can actually put that.
Of course. Yeah, and so we just graph. And here is my graph. Looks pretty much the way I graphed it, yes. And if I want more points, I want to be more precise. As before, I just go to my second table or second graph to get the table, to get my values. And here you go, right? Just take good points, 0, 1, 1, 3, 2, 9, negative 1.3, negative 2.1. And I can do it this way.
Wait,
Hmm?
what does that fraction out to?
Which one? What do you mean?
The 0.3 and 0.1.
Here, I took this, right? Negative 1.3, and then because it's repeating,
Yeah, but what would its fraction
this one is
counter-
1 over 3, and this one is 1 over 9.
Okay, I just want to make sure because
Yes.
I put the fractions in.
Questions about this? Perfect. So now let's remember this one, right? This is our parent. How can we do this so that I see it? Okay.
So there are no transformations.
So yes, because this is the parent itself, yes? What if I do this? See, I'm getting fancy and copycat group. And then copy. I just want to take it with me to the next slide because you have it and I don't. Right? So now, let's do the second example. Y equals 3 to the power of x to the power x minus 3. So what is my b? Still 3. So what is my parent function? Y equals 3 to the power of x. So
But
this
the
is my parent function.
minus 3.
No, the parent.
Minus x. I mean h. Minus h.
No, the parent function for this one, right? If I go back to our notes, right? So we start with the parent function y equals e to the x, and then we apply transformation. We have a and h and k, yes?
Mm-hmm.
What
So-
you apply before
Right, so if my parent function is just b to the power of x, which is this was the first example, what are the transformations that we have here? Right, d, that's it. So what do you think is it growth or decay?
Growth.
Still grows. Same b, still grows. But it's greater than 1. What do you think the horizontal asymptote will be?
Yeah.
It's still the same, y equals 0, right? Because all I will do to this function is move it to the right. So the horizontal asymptote will not go anywhere. So my horizontal asymptote is still y equals 0. It's still here. What about domain? Will it change? Still all real numbers. What about my range? Still the same, right? Because horizontal asymptote is still the same. It's still 0 to the positive infinity. And by the way, why don't I put brackets for this 0, for range? Kevin, why don't you put brackets? Because we never reach the asymptote, we never cross it, right? We get very close to the asymptote, but we never cross it. So we never reach that 0. Does everyone understand? Yes. Why horizontal asymptote is still 0? This is 0. This. I'm sorry, that's my amazing handwriting. I'm sorry. Still 0. So very carefully with those brackets versus parentheses, right? Because we never reach or cross horizontal asymptote. That's why we don't include the 0 in the range. That's very close, but doesn't get to cross it. Okay. So what about y-intercept? So we know that x equals 0, right? For that point where my line crosses the y-axis. So it's 0 something. And so to get the y value, I just need to plug the 0 in. So here y equals b to the power of negative 3, which is 1 over what? 27, correct? Which is a very small number, 1 over 27. Y-intercept, yes? I'm just plugging in 0 instead of x. Am I going too fast? So we are going to this third example. What is my b here?
3.
Same, 3. So what is my parent function? 3 to the power of x. If I know my b, I know my parent function. What are my transformations here?
Left 4 up 2.
Left 4 up 2. So growth or decay? Lily, growth or decay? Growth, right? Because b is still 3 more than 1, so this is again growth. What is the new horizontal asymptote, Eva? So my function will move to the left 4 and up 2. So my old horizontal asymptote was y equals 0. What is the new one? Y equals 2. Either figure it out from transformations or look at our cheat sheet, right? Y equals k. My k is 2. Yes? I'm going to graph it. Y equals 2. Okay, so what is my domain?
Negative 32 infinity.
Still all real numbers, negative infinity to positive. Now, will my graph be above or below my horizontal asymptote? Above. So what is my range? 2 to infinity. There is no negative, so I know it's above. And again, so now we can still use transformations to graph it, right? Or we can do the calculator. What do you want to do?
Wait, what's the y-intercept?
I will figure it out.
Okay.
Transformations, okay. So for every one of these points, let's say 0, 1, my point will go, what is it, 4 to the left, so my x should be negative minus 4, right? And then up 2, so 1 plus 2, 3. So you see, my point 0, 1 became negative 4, 3. Yes? I moved my point 0, 1. It should go left 4, up 2. So negative 4, 3. See what happens? Yes or no?
Yes.
I'm just taking point by point. So because my whole graph goes left 4, I need to do x minus 4 from the original minus 4. So instead of 1, 3, I'll have negative 3,
Isn't it
and then
negative
it goes
4?
up.
Because you do it to the left.
Huh?
0, negative 1, negative 2, negative 3, negative 4.
Yeah, so negative 4, left 4.
Oh, never mind.
Yeah.
I miscounted.
And then up 2. So up 2 will be 5. From 1, 3, I moved to the left 4. So 1 minus 4 is negative 3. And I moved up 2. So 3 plus 2 is 5 now. Yes? You look confused? Are you confused?
No.
Good? Yul, are you good? Yes or no? Kind of? You know what? Or just calculations, right? I mean calculator. Always an option for the graph, yes?
Yes, ma'am.
Calculator, that's it. Or do it with me. So minus 5, minus 6, and this plus 2 plus 2. So 2, 1, 2, 3, 5, and then 11.
Does
This
that
is how I
mean
know.
is it?
I'm applying transformations to mine.
I know, but 2/3.
It's not 2/3. It's from point 3. It became 2.3 because it moved up.
I
So
know, but
plus
I
2.
want to know what the fraction point is.
Oh, this one?
Yeah, is that 2/3?
So this will be 1/3. No, this would be 2 plus 1/3. So it's 7/3.
Okay, so then the
2
other.
and 1/3, right? And then this one would be 2 and 1/9. Okay, so plot in my points. What is my point? Negative 4, 3. Oh, this is impossible to see. Negative 4, 3 right here. Then negative 5 would be less than that. And negative 3. Oh, 1, 3, 5. Yeah. And then this one gives me 11. Okay, so something like this. Not very precise, but good enough. Yes? So it's the same shape, it's just I moved it up 2 and left 4. So the final question, y-intercept. How do we find it? So either we substitute 0 for x, so y equals 3 to the power of 0 plus 4, which is just 4, and then plus 2. 83, right? No. Because 3 to the 4 is 81 plus 2, 83. So it's 0, 83. Or if we use calculator, we just go to the table and look for the point where x is 0. Yes? Everybody with me? Yes. Okay. Questions? So do the next one by yourself. I'm just going to silently put my answers here.
getting really tired of 3.
I know. I just wanted you to compare all these functions to the parent. How they're all different.
Huh?
Check your answers. Are we good?
That is perfect.
Okay.
No.
So let's quickly do this one together. No, go back, go back. Mhm.
-1 to the y.
For the y-intercept, so for y-intercept we know that x is 0, yes? Yep. So let's check. Y equals negative 3 to the power of 0 minus 2. What is 3 to the power of 0?
Oh, I didn't put the negative in.
Ah. Any questions? By yourself? Yes. Okay, I'm going to put the answer.
Should we put the decimal?
Yeah?
That's okay.
Yeah, first. Check your answers.
Have you done yet?
Euler's number. No.
No.
So Euler's number is one of the most important numbers in mathematics. If you study mathematics or engineering or science or whatever, calculus, differential equations, probability statistics, you will see this number over and over again. So it's called Euler, and we use E, letter E, small e, to represent it. Like pi is the number, right? This is E. It's a rational number, which means what? What is a rational number?
It's not real. It's not rational.
No, it is a real.
But it's not rational.
It's not rational. What does it mean in English? Cannot be represented as the fraction. Cannot be represented. There are no such n and m that could give you this number when you like. That's what the rational number. Okay, so this number is approximately 2.718. Approximately.
Sounds like pi.
Like a pi, yes. Kind of like a pi.
Beautiful number.
E is even more beautiful than pi. This is the most beautiful number ever.
Pi
E.
is the most beautiful number.
No, it's a
Yes,
E.
no.
There are books written on E.
There are books written on pi.
No, but E is like everywhere in the universe.
Pi is everywhere in the universe. There's a
Oh,
pi
no,
K.
E.
There's a pi K.
You need me to pi is my birthday. What do you need?
Actually, it's
3
4
for
days away.
10, yes.
One.
Yes.
March. Cool.
14.
Okay, so E on the calculator can be found by second division. So if you look at the calculator, in the calculator, if I wanted to say E here, so second and right here, CE. That's your number. Or if you want to e to the power of 2, for example, then either like this and then to the power of 2, or there is a shortcut also. Clear, clear, clear. You see here second ln, yeah, and then just
On my calculator, 5 is above
second
5, but
division to get just e, or second ln to get e to the power of. Yes? Found it? All right. So very often when you use, or yeah, when you, I guess, model something with the exponential function, you will use the base e very often. And everything stays the same, right? All the properties of the exponential function are all the properties of exponential function. So the b, if we have a function y equals e to the power of x, what is my b? E, which is what? Approximately 2.718. So is this exponential growth or exponential decay? Growth, right? Because my b is more greater than 1. So everything stays the same. You just need to remember that e represents specific number, which is approximately 2.718. So no time to talk about this really, but just know that e, yeah, I wanted to have it, but we are running out of time. So just remember that many applications. If you go to finance, you will use e like everywhere. Every single formula will use e. Because it's all about continuous compounding of interest, right? You earn interest of 1 cent, it's already earning interest, and it's like continuous compounding, it doesn't matter. If you study biology, that's how bacteria or cells grow, right? So if you want to know more about it, there is this really cool video you can watch. It's like 7 minutes or 9 minutes or something, and it's very intuitive explanation of where, like, why is it, like, what is explained. It's really nice. And then, you know what? No time. Fine. So how can we calculate? There are many different ways you can use, but none of them will give you the precise number. I think they know like up to million or something digit after the digital point, but not after that. You can approximate it that close, but you can never get the exact. One approximation, good approximation, is if you take the function 1 plus 1 over n to the power of n, and you evaluate this expression for different n's, then 1, 2, 3, 4, 5, and so on, your result will get closer and closer to e. So that's one of the. This is very related to finance and biology. Like this is the natural growth. How to model natural growth. But anyhow, this is just like to expose you to this. If you want to know more, and if you want to talk about this Gambler example, just talk to me after class. It's really cool. Okay, so now, well, let's just grab this one. We already said these our E, which is approximately 2.718. So, what is the parent function?
Y equals dx.
Yeah. There's no transformation happening, right? This is the parent function. Growth or decay? We already said it. Growth. Because my b is greater than 1. What is the horizontal asymptote? 0. I almost send it. Domain? All real numbers. I go very quickly here because, I mean, this is just another base. We just change the base. And the range? 0. So you can enter it into calculator. Or you can just write it, I mean, approximate shape. You will not be able to do it much exact. I'll just do the approximate. So if my x is 0, then my y is what? 1, right? Because anything to the power of 0 is 1. So I know at least 1 point. Then I know my horizontal asymptote. And I know that when x is 1, it will be e, which is almost 3. So somewhere here. So pretty close approximation will look something like this.
These are horrifying numbers.
These are what?
Horrifying numbers.
Horrifying
They're
numbers.
terrible.
They're beautiful numbers.
Are they all going to be like this? Every time we use E, are the numbers going to be like this?
Yeah, because e is not an integer, right? So it will be
That hurts.
horrible numbers, yes. Every single time you use e and take it to the power of, it will be a horrible number. But the function is beautiful, I promise.
Oh, guys. The only phone number
It
is 0.
explains so much. Questions about this?
Is there a homework?
No.
You
Okay.
can give it to us.
I gave it to you, yeah? Oh yeah, we shouldn't have.
No, you should have, because I was on to say late.
Okay, so should we do this one? Yeah, let's do this one. Number 7. You know what? Let's do number 8. Here, let's just do a couple of things. What is my base function here?
Number 7 is so
Number 7. Let's just do like a couple of things. Oh, hard? You said hard? Oh, it's ugly. Oh. No. Okay, so what is my b? My b is my b. E. Careful. My b is e.
So
E to the power of. So my parent function is what? Y equals
dx.
e to the x. Very nice. So what are my transformations?
compresses.
Compress. See, now I have this a, right? This is my a.
Down 3.
A. So compress
Down 3.
and then down 3. Gross or decay?
Because
Gross. Based
What?
on B. It's B. It's all about B, not A. I don't care about what's in front. So gross. B is more than 1. Ignore the A. Gross. Horizontal asymptote.
Oh, you're right. It is greater than 1.
Horizontal asymptote.
0?
Negative 3. Domain.
what?
Domain.
Negative
Negative 3 to
3.
infinity all around.
All real numbers.
Wrong one.
Negative 3 to infinity.
Range negative 3 to infinity. Do we agree negative 3 to infinity for range?
I'm going to break this one.
So my asymptote y equals negative 3 right here. And then since we don't move right or left, kind of quite easy to approximation. This is rough approximation just to get the shape. If I wanted to be more precise, I would enter it into calculator, get the points. Very nice. So even though the points are ugly, you just round them.
Yeah, they're all.
Yeah, but just round them to like one digital point after. Should we do this together, calculator, to see how we round them? Should we do that? Calculator. Let's just do this.
Yeah,
Let's do this. Okay, so I go to y equal again. And then I enter, remember, fractions in parentheses. Fractions in parentheses. So 1 divided by 2. And then I have my e to the power of x. And then minus 3. So I graph it. Similar to what I have my graph approximation. Now I go to second graph to get the table. Very ugly, but I don't care. Yeah? So, very ugly, but I don't care. Because I can just use, round. I mean, it will never be perfect. But I can kind of see it. So 0, negative 2.5. So 0. Why is it 0, negative 2.5? Oh, that's right. So this, yes. So 0, negative 2.5. So 0, negative 2.5. That I can do. And then 1, negative 1.6. Which I mean, the precision that I will be able to do here is like 1.5, negative 1.5. So 1, negative 1.5, somewhere here. And then 2 point, approximately 0.7. So it's above the line now, but not quite 1. Something like this. You see, I'm just like looking at the closest, like round to 1 digital point. And I think my dots, every point is like better than the whole cell, the whole thing. Questions? Questions?
So funny.
No, plug it in.
She doesn't